It's hard to argue that observability is anything but a good thing, but it can also be a challenging thing, particularly in distributed and even more so microservice-based systems. It's also often left as something as an afterthought in the development of new features and systems. So what do we mean by observability? What are the challenges that it poses in development, and specifically what are the extra challenges and importance for microservice-based systems? That's our topic for today. Hi, I'm Dave Farley of Continuous Delivery and welcome to my channel. If you haven't been here before, please do hit subscribe, and if you enjoy the content today, hit like as well. Observability is not a new idea, but it has become more topical to talk about it in recent years. I'm sometimes asked what I think the difference between engineering and a more craft-based approach to software development really is. And my simple answer is measurement. And for that, we need measurable systems. And to make them measurable, we need them first to be observable. That is, that it's possible for us to observe them and see what they do, and understand what they're doing and how they're working in production. The definition of observability in software terms is the ability to collect data about a program's execution, modules, internal states, and the communication between its components. If you're a regular viewer of this channel, you will already know that I believe that it's important to adopt a more incremental, more experimental approach to development. To support that, we need feedback on how well our choices in terms of the technicalities of our designs, but also of the functional product level decisions that we have already made, are playing out. Certainly, for some of these things, we can get that feedback from tests before we release. But for others, we can only learn these lessons that we'd like to learn from observing what actually happens to our systems in production. This is what I think of as the empirical learning that is a fundamental part of a good, stronger software engineering-based approach. Let me pause there and say thank you to our sponsors. We are fortunate to be sponsored by Equal Experts, Transfic, and Semaphore. All of these companies offer products and services that are well aligned with the topics that we discuss on this channel every week. So if you're looking for excellence in continuous delivery and software engineering, do click on the links in the description below to check them out. One of the most frequent comments that I get from my videos is that people like my t-shirts. So we reached out to the company that I buy most of my t-shirts from, QWERTY, and they've given us a discount code for viewers of this channel that you can use to get 10% off any t-shirts that you buy. Enjoy the shirts and let us know which one you bought in the comments. Observability is a property of a system. It's not a tool or a technique, and this isn't a binary thing. The degree to which a system is observable changes what we can do. We need to get the signal to noise ratio correct. Too much information is nearly as bad as too little. But we also need information about different aspects of the system. And I think that this is one of the things that has changed more over recent years. It used to be that when we thought about how to observe our systems and how observable they were, we mostly thought in terms of monitoring the more technical measures of its performance, CPU usage, disk space, and so on. But these sorts of things are just one aspect of what's really interesting, and not the most interesting. If our aim is to understand what is really happening in production, we'd also like to know how people are using our system and what value it's adding to them. At a more technical level, observability is commonly described as being composed of three different types of telemetry: metrics, logs, and traces. Metrics are the measurements that we take. The value of the CPU usage, the number of trades per second, or the number of new users that are currently using our latest feature, and so on. A metric is a measurement in a moment of time. A log is a log of events, a sequence of things that have happened, often but not exclusively kept in a human readable textual form. A log is a good way to keep track of the details of significant decisions made or errors experienced during the course of the operation of our system. Logs are often used to identify the cause of problems after a failure, recreate bugs, or to predict problems that the software may be heading towards. The last category of observability is traces. Traces map interactions across a distributed system, a series of breadcrumbs that allow us to follow how the system was used. which services were visited in fulfilling a particular function of the system perhaps. This is obviously useful knowledge to have, but not always easy to see, particularly in microservice-based systems. Because in a system developed as a collection of microservices, the main point of this architectural approach is the scalability of development teams, meaning that a microservice-based system is built by a number of loosely coupled teams, each working more autonomously with respect to one another. The result of this is that consistency across services is not necessarily one of the strengths of a microservice approach. That means that tracing the route of interaction across services can be complicated, but we'll come to that. In fact, all of these things are much more difficult to achieve in distributed systems in general. What do metrics like how many users are using feature X, or what's the CPU usage, or even average response time really mean if we have multiple concurrent services contributing to that answer? How can our logs tell the truth of a system when we have distributed services processing things in parallel and spread across many different services? Even if we timestamp every entry, are we certain that the clocks are all in step? How can we identify and so trace which versions of which services processed a part of an interaction? None of these things are simple problems, and they can have a big impact even for simple versions of observability. When we adopt distributed approaches to systems like microservices, in a microservice solution, we often have lots of different services and lots of copies of the same service, often operating in an ever-changing cloud of relationships and dependencies. Because each service is deployable independently from the others, so may be changing or being updated at any time. The simple view of things is that there is a fixed route or order for conversations between our services, but part of the value of microservices is that this is not necessarily the case. Microservices, particularly my preferred flavour of microservices, event-based asynchronous services, allow us to add, replace, remove or reorder behaviour all fairly easily. But while these changes may be easy to make, their implications for being able to understand what happened, our observability of the system as a whole, is not so easy. To make this work, we need to adopt what I think of as a series of more distributed approaches to observing what's going on. We need the ability to dynamically stitch together a coherent picture of the system from a series of distributed discrete pieces. This problem of application rather than service scale metrics is a really quite tricky one, but it is one that we need to tackle for systems like these. Let's imagine the simplest possible case. We've got two copies of the same service, one running in a data center in London and another in New York. How many new users registered for our service between the hours of 2 p.m. and 4 p.m? That's a really easy question to answer if only we had one service, but given our example, not quite so easy. We may ask, whose 2 p.m. and whose 4 p.m. do we mean? Because these services are running in different time zones. We could interpret this as 2 till 4 in London, 2 till 4 in New York, or 2 till 4 local time for each. And all of those might be the right answer depending on what question we wanted to answer. Time is equally a problem for logs and traces though, not just for these sorts of measurements. If service A writes a log X happened at 12:01 and B writes Y happened at 12:02, which one came first? We can't tell with only that information. We'd need to know about which time zones they were in, including things like daylight savings adjustments in play. We'd also need to know if the clocks were synchronized or not. Time is a problem and not an easy one in concurrent systems. What does concurrent mean anyway? And at what resolution of time does all of this matter? These may seem like esoteric questions, but there are simple questions that we simply can't answer unless we worry about some of these esoteric things. Did A happen before B? If we can't answer basic questions like that, tracing the use of our system and establishing a coherent distributed log is impossible. There are a few common patterns that can help us though, to overcome these problems of observability in distributed systems. The first is maybe obvious, but time synchronization. This can take a variety of forms. Which form works best depends on the nature of your system and the resolution of accuracy that you really need. But the idea is that you establish a common baseline for all of the clocks and stick to it. It's generally a good idea to store all timestamps in Universal Timecode, UTC. Then it's easy to convert times from UTC to your local time or whatever other time zone you need. But as well as agreeing on your time zone and communicating and storing times, you also need to synchronize all the clocks so that they tell the same time. There are protocols that help us to achieve this, including for cloud-based services to synchronize time between your servers. But even this may not be enough for some systems. NTP, on which most time synchronization systems are based, provides time synchronization at the level of milliseconds. But what if you need to determine the order of things to the nearest microsecond? This stuff can get pretty complicated. Another approach to establish a current view of the state of things is to take a snapshot. Ask distributed resources to report their state at a specific time. A good example of this, and another useful microservice pattern, is a health check. Every service supports a health check, which we can poll. We use this approach in our financial exchange at LMAX. We'd check these health checks on a regular basis, asking for a status report from every service every 30 seconds or so. I'd always prefer things like this to work on a pass-fail basis, healthy or not, so each service has a built-in model of what healthy means for it. We made ours hierarchical, so if one service depended on others to do part of its work, it would pass the need for a health check onto its dependencies. That meant we could traverse a graph of services and build up a comprehensive view of the overall health of the system. We'd report the cause of health failures in response to these health checks, so that then we could diagnose problems more easily. In distributed systems like these, establishing a coherent picture is complex for several reasons. Time, certainly, but also where to look for an answer when tracing. Local logs is no good in terms of ease of access or consistency of the overall picture. Okay, we got to this service on this server, then it sent this message, but where did it go? To solve this problem, we need another useful pattern, log aggregation. Instead of each service or component of the system writing log entries locally to a file, we need to establish some central point that collects logs and assembles a system-wide account of what really happened in what order it happened in. There are tools that support this kind of thing very well, but with good pub/sub messaging infrastructure, it's really not that difficult to establish your own custom versions with a little thought if you need to, which can be very helpful for other less generic forms of logging. For example, you could log a searchable database of global order history for later market data analysis. Time is certainly one problem when attempting to piece together a sequence of distributed events in a microservice system, but another equally important one is context. Is this event related to customer A for order 51 or customer B and order 52? For this, another useful pattern is that of correlation IDs. A correlation ID is what it sounds like, an ID that allows us to correlate information. US citizens will be very used to using their social security number to uniquely identify themselves in a variety of contexts. This is a correlation ID, so we need to build a model of ideas that define the context that we are interested in. We may even need to build a model of relationships between those IDs so that we can uniquely identify things that are lower down the hierarchy. One way to think about this in the context of microservice is described in this video. We can model the relationships between things, build a model of keys and their relationships, and use those keys to define separate different conversations in the system. For that to work, we need every message to contain the relevant keys that contextualize the conversation so that we can piece it all together later. This allows us to maintain a coherent picture across distributed interactions. As long as the services share this context model, we can correlate the work of any number of services, even when they are independently developed and deployed. Observability is important to maintaining our ability to monitor our systems in production and learn from them. In microservice and other distributed systems, none of this is simple though. Using techniques like these help to make it easier to maintain a coherent picture. of what is happening, and so provide us with a powerful and essential tool to maintain and grow our systems in production. Thank you very much indeed for watching, and if you enjoy our stuff here on the Continuous Delivery channel, please do consider supporting our work by joining our Patreon community.